Hi, this is Stephen, and today we'll discuss how the principles of conservation of flow and conservation of mass can be used in echocardiography. So first, with conservation of flow, the equation that we use is the cross-sectional area times the velocity at a first point is equal to the cross-sectional area times velocity at a second point. And the units for this cross-sectional area would be centimeters squared times centimeter per second equals, again, centimeter squared times centimeter per second. So this is talking about centimeter cubed per second, or flow per time. And what does this mean? Well, if you were to look at the heart and you have blood coming in at 5 liters per minute, and let's say it were coming out at 4 liters per minute, that would mean that every minute 1 extra liter of blood was filling up the heart. And it would, after 5 to 10 minutes, it would explode, right? This is not sustainable. So whatever flow is coming into the heart needs to be the same flow that is coming out of the heart. So if it's 5 coming in, it has to be 5 going out. The idea of the conservation of mass is very similar, but we use a slightly different equation. So for conservation of mass, we use this equation. We say the cross-sectional area at a first point times the time velocity integral, you may remember that from our previous video, at that point equals the cross-sectional area at a second point times the time velocity integral at a second point. And the units for this, centimeter squared times centimeter equals centimeter squared times centimeter. So it's centimeter cubed, or a volume. And it's really the same idea. If you have 70 mil of blood that came into the heart in a single heartbeat, that same 70 mil of blood needs to leave. Otherwise, after a couple of minutes, the heart will have shrunk all the way down to nothing, or it will have expanded and exploded. So whatever comes in, whether it's in a given heartbeat with conservation of mass or over a certain time period, like a minute, if we're talking about flow, whatever comes in needs to go out. All right, how can we use that? Well, we can actually use that to quantify aortic stenosis. So let's look down here at aortic stenosis. And let's look in our apical 4-chamber view. So we've got our left atrium that empties into the left ventricle. Over here you've got the RV, RA, and we're going to tip that probe so that you can also see the LVOT and aortic valve right there in the so-called 5-chamber view. And then let's measure the velocity right at the LVOT with pulsed wave Doppler. Pulsed wave Doppler measures the velocity at a particular point. And we'll get a graph that looks something like this. Every time the heart beats, you'll see blood flowing out, blood flowing out. The units on this, here we have time in seconds, and this would be, let's say, meters per second. And if you integrate this, that'll give you your time velocity integral. Let's say that's 25. And let's say that that'd be 25 centimeters. And let's say that our maximum velocity here, if you just look at the number, when the blood is flowing at its fastest, let's say that is 1 meter per second. Okay, now let's do a second measurement with something that we have not discussed yet, called continuous wave Doppler. So continuous wave Doppler, you're measuring the velocity all the way along this line. In particular, you'll measure the velocity at wherever it is the highest. So this is continuous wave Doppler, and the question is why? Well, if you look at blood flowing out the LVOT, you see it would be something like this. So first you have blood that's flowing here at ordinary velocity. This is in the LVOT. And then as blood flows through that narrowest portion of the aortic valve, it has to really go much faster. Right? It's like traffic when there's 3 lanes and now there's only 1 lane. It has to go much faster before eventually, once it's into the aorta, it'll then again go at a normal pace. Now, the beauty of our continuous wave Doppler is we are measuring all of these different velocities. And so we will also be able to catch this high velocity, even if we don't put a cursor right at the exact point. So what will we see with continuous wave Doppler? Well, we'll again see a graph with time and velocity, but the values may be much higher. In particular, this Vmax might be 4 meters per second, and our TVI here might be 100 centimeters. Now, how can we use the continuity of, how can we use the conservation of mass or conservation of flow to our advantage to quantify how narrow that aortic valve is? Well, let's write down those equations that we discussed. So we have the area at the LVOT times the velocity at the LVOT is equal to, we don't know what the area of our aortic valve is, that's our unknown, times the velocity at the aortic valve. What numbers do we have for this? Well, the area of the LVOT, let's assume that it was LVOT diameter of 2, as we talked about in the previous video. So pi times radius squared would be pi times 1 squared. And again, we measure that from the parasternal long axis view. And then what's our velocity? Well, our velocity was 1 meter per second. And we're going to divide by our velocity, our Vmax, that we got with the continuous Doppler. And what does that give us? That gives us, so it's basically pi divided by 4. That's about 0.75 meters squared, centimeters squared, sorry, which would be severely stenotic. Anything less than 1 square centimeter is severely stenotic. So that's using area times velocity equals area times velocity. Again, if we look back here, that's conservation of flow. How about if we use conservation of mass? The idea that the same chunk of blood that is pumped out into the LVOT, that blood all goes through the stiff and narrow aortic valve. None of it is going to some other place. Well, in that case, we're going to have this equation, namely the area at the LVOT times the TVI at the LVOT equals our unknown, the area at the aortic valve times the TVI of the aortic valve. And we can solve here. The area of the LVOT is pi r squared, where that would be pi times 1 squared times, what do we say we said our TVI was 25 at the LVOT, divided by a TVI of 100 at the aortic valve, which will give us, again, pi over 4, which will equal about 0.75 centimeters squared. Again, a severely stenotic or narrow aortic valve. So using this principle that all the blood that flows at the LVOT also then goes through the narrow aortic valve, and looking at how the velocity or the VTI change at those 2 points, we can calculate the cross-sectional area of the aortic valve. Now you may wonder, which of these should I do? And the truth is we often prefer the VTI method, because if you look back at these graphs, with VTI, I'm actually looking at the area of this whole, I'm taking the area under the curve, versus with Vmax, I'm just looking at a single point. And if that single point was measured incorrectly, my whole measurement may be wrong. So if you have both, we often prefer using the TVI method.